So we were talking about HMO approximations, and in the previous module I was talking about Butadiene system. Butadiene system, as you have seen, it's a 4 pi electron system. So after the linear variation treatment, what you get is 4 by 4 determinant. This 4 by 4 determinant on solution gives you different x values, and from that x value we found the different energy levels, bonding molecular orbital and anti-bonding molecular orbital. So we get 4 different energy levels, and obvious, since from the beginning I'm saying it time and again that both alpha and beta are negative quantity. So the bonding molecular orbital has energy alpha is plus 1.618 beta. Then another bonding molecular orbital has energy alpha plus 0.618. Both are alpha and beta are negative quantity, so it will be more negative values of energy. If you have alpha minus 0.618 beta, then it will be certainly negative, maybe negative value, but higher than the one of the value will be positive, another value will be negative. So this will go to anti-bonding molecular orbital. Again here also one value will become positive, minus 1.618 beta will become positive because the beta is negative, and alpha will remain negative, so it will be higher value of energy. So for anti-bonding molecular orbital, if we draw the energy level diagram and fill the electrons, because we have 4 electrons here, so what is the energy level diagram? This is the energy level diagram for butadiene molecule. We have both E1, E2, E3, E4, all the 4 energy levels are there, and both the bonding molecular orbitals are occupied molecular orbitals. Okay, and so E2 is the highest occupied molecular orbital. If we calculate the energy of these 2 electrons, then 2 electrons you have in E1, so 2 electron alpha plus 1.618 beta, and 2 electrons you have in the E2, so 2 into alpha plus 0.618 beta will be the total energy of the 4 electrons present in the bonding molecular orbital of butadiene system. Okay, so total energy of the butadiene system is equal to what? If you calculate this one multiplied by 2, so it is 2 alpha plus 3.3236 beta plus 2 alpha plus 1.236 beta. So 2 alpha and 2 alpha will be 4 alpha, and then add the beta terms, 4.472 beta is the total energy of the total pi energy of the butadiene system. Okay, we have 4 electrons here. So if you look at the 2 ethylenic bonds, then one of the ethylenic bond will have energy equal to 2 alpha plus 2 beta. Okay, will be the energy for ethylenic bond for two ethylenic bonds will be equal to 4 alpha plus 4 beta, and so if you subtract this one, you will get the delocalization energy. So the difference between this is the delocalization energy you get by restricting the movement of pi bond, or you say by placing the pi bonds between C1 and C2 and a single bond. This, if the bonds are localized between C1 and C2 and C3 and C4, then the energy is 4 alpha 4 beta, and if it is delocalized over the whole system, then the energy is 4 alpha plus 4.472 beta, and that's how you get delocalization energy. So the delocalization energy is 0.472 beta, which is a negative quantity, and this tells you that when you do the delocalization leads to stabilization of the system. Okay, or the system gets stabilized. Now for finding, so this way we have got the energy level, so eigenvalue we have obtained. The next task is finding out the eigenfunction, and for finding out the eigenfunction, as we have done for allyl system and cyclopropenyl system, we will do the same thing with the butadiene also. In case of butadiene, we have 4 by 4 determinant, so we can write 4 different equations for each row of the determinant. And you look at this one, the first row of the determinant has only 2 terms, x1, and rest 2 terms is 0, 0. So the terms, so the term which you will write is, this c is not there. Okay, so a1x plus a2 is equal to 0. Okay, and then you have a1 plus a2x plus a2, second row will be a1x plus a2x plus a3 is equal to 0, 3 terms. Then in the third row you have again 3 terms, but it starts with a2. A2, A3x and A4. A2, A3x, A4 is equal to 0. And in the last row again you have only two terms, that is A3 and A4. So A3 plus A4x is equal to 0. So these are four simultaneous equations which you can write from the secular determinant of butadiene molecule. So what you need to know, since our psi MO, which we ultimately we have to write, is A1 psi 1 plus A2 psi 2 plus A3 psi 3 plus A4 psi 4, okay, where psi 1, psi 2, psi 3, psi 4 are the wave functions for 2p z orbitals, okay, because you have sp2 hybridization for the butadiene system, and each of these carbon atom have one pz orbital. So this psi 1, psi 2, sometime I have written phi 1, sometime I have written psi 1, so it's the same thing, the only representation is different, don't get confused with that one. So A1 refers to coefficient and psi 1 refers to one of the pz orbital of one of the carbon atom, okay. So what you have to find out, for finding out the eigenfunction, you need the value of A1, A2, A3 and A4. That's why in every case HMO coefficients we find out. And for finding out these coefficients, we already have the x value, so this simultaneous equation will change for each of the x value, because you have four different x values. So you can put the same one of the x value in these, and you will get a set of four equations. Then another value you can put, and then again you have a set of equations. This you have done earlier, so I hope it will not be a problem. So what we can write, for x is equal to minus 1.618, what I can write is minus 1.618 A1 from the equation number 1. If I say it is equation number 1, so from equation number 1 you get this one, okay. Then what does it mean? It means A2 is equal to 1.618 A1. Then the next equation is equation number 2. So from equation number 2 you write this equation, A1 minus 1.618 A2 plus A3, and what does it mean? It means A3 is equal to minus A1 plus 1.618 A2. See, A3 is equal to minus A1 plus 1.618 A2, and so what you can write, A2 value is already there, so take an A2 value from here and then put it at this point, okay. And finally what you get is A3 is equal to minus A1 plus 2.618, so 2.618 minus 1 will be 1.618 A1. So A3 is equal to 1.618 A1 we got, okay. What does it mean? A2 is equal to this one from these two equations. This equation, A2 is equal to 1.618 A1, and A3 is also equal to 1.618 A1. So A2 and A3 are equal. Net result is A2 and A3 are equal. So this we obtained. Now what we do is that we write A3 minus 1.618 from equation number 4. This is your equation number 4. From equation number 4 you can write this one, A3 minus 1.618 A4, and so A3 is equal to 1.618 A4. And if it is so, then A4 you can write as A3 divided by 1.618, and A3 is what? A3 is 1.618 A1, okay. So put 1.618 A1 divided by 1.618, and what do you get? What you get is A1 is equal to A4. This and this will go. What will be? A1 is equal to A4. So what we got is two important relationships. A2 is equal to A3 and A1 is equal to A4. From these simultaneous equations we obtain, okay. Once we have this one, then what you can do, let A1 is equal to 1, okay. Then A4 is equal to also 1, and so A2 is equal to A3 is equal to 1.618. Let A1 is equal to 1, so A2 is equal to 1.618, and A1 is equal to 1, so A3 is also 1.618. So that's what I have written. A1 is equal to 1, then A1 and A4 are equal, so A4 will also be equal to 1, and so A2 and A3 will be equal to 1.618. And your equation will be, wave function will be, we have supposed A1 to be 1, A4 to be 1. This is not the actual value. So I have given a constant here C1 multiplied by psi pz1 plus 1.618 psi pz2 plus 1.618 psi pz3, because A2 and A3 are 1.618. This is the relative value. If A is equal to A1 is equal to 1 and A4 is equal to 1, then you can write this particular eigenfunctions. Okay. Now for normalization condition, what will happen? For normalization condition, again the same equation you will obtain, A1 square plus A2 square plus A3 square plus A4 square is equal to 1. And if you use, see, in every example there is some distinct things which you should notice. It is not at all the repetitions of the same thing. Previous to this one, we never came across with this one, substituting A1 and A4 relative value and then finding out the value of coefficients. So in every example which is there is some new concepts involved. So you should do it on your own along with a pen or paper. You watch the video and you must practice it. Otherwise, you will forget it, that how it was done. Okay, and these are very simple calculations which anybody can do. So from the normalization condition, what you get is A1 square plus A2 square plus A3 square plus A4 square is equal to 1. And now if you use this one relative values, then A1 square is equal to 1, A2 square is equal to 1.618 square, A4 square is equal to also 1.618 square plus 1 is equal to 1. And if you write this one, then total value is 7.236 C1 square is equal to 1. So C1 value we can obtain. So C1 value is, C1 square is 0.1382 and C1 is equal to 0.372. Now if you multiply with this C1 value here, you get the actual coefficients of A1, A2, A3. So what does it mean? If C1 is equal to 0.372, means A1 is also 0.372, A4 is also 0.372, and A2 and A3 will be this 1.618 multiplied by 0.372. And finally what you get is 0.372 psi pz1 plus 1.618 psi pz2 plus 1.618 psi pz3 plus psi pz4. And if you multiply this, obviously what you get is 0.372 psi pz1, and if you multiply 0.372 and 1.618, what do you get is 0.602. You can do it yourself and check it. Okay. So 0.602 and 0.602 for P2 and P3, and for P4 again 0.372. So finally the first wave functions which we have obtained is this one. Okay. Now once you have the wave function, see all positive sign you have, no negative sign you have. So all these wave functions you can write. Okay. Psi 1 is equal to this one. Similar calculation with other values of x will give other energy level wave functions. I did not do other functions because we have already done many calculations, and I've just written the value of psi 2, psi 3 and psi 4. Okay. So psi 2 value comes out to be 0.602 P1, PZ1 actually, and then plus 0.372 minus 0.372 minus 0.602. Okay. That you should practice, that how will you get these values, because it's the same value, similar value you should get by placing another x value. See, x value was when I started talking about placing the value of x is equal to minus 1.618. But how many values we have? X value we have, let me see, x value we have is 0.618. The first slide, I think. No. So this is what is x value. You see, 1.618. In another case, so with the plus value we have determined, minus value you can do, and then again with 0.618 also you can do. So the value which you will take in each of these cases, this will obtain. In one case it will be minus 1.618, in another case it will be 0.618, then again minus 0.618, and so all these wave functions we can obtain. See the value, the coefficients value, it's only two values is there, either 0.372 or 0.602 with a plus or minus sign. Okay, no change in the no other value you get. Always what you get is a 0.602 and 0.372, but the sign is changing. Here it's plus, here it's minus, minus, here it's minus, here it's plus, here it's plus, here it's minus. Okay. So all four eigenfunctions one can obtain in the similar fashion by placing x is equal to minus 1.618, x is equal to plus 0.618 and x is equal to minus 0.618. These three calculations knowingly I have left for you to do it, okay, because we did ethylene system, we did allyl system, we did cyclopropenyl system, and now we are doing betadiene system. So by now you are aware of these calculations. If you have done it previous results, then you can calculate this also. Okay. So try to find out whether these results are right or wrong, and you check it out. Okay. So these these are the four different molecular orbital wave functions for betadiene molecule, which is obtained by HMO approximations. Now, if once you have these bonds, then the next task which we are doing for every molecule is calculating electron density, charge density, and bond order. So in electron density, what you do, you consider only those orbitals whose energy where the electron is present. So we have four different energies, two bonding and two anti-bonding molecular orbitals. So one of these, two of the bonding molecular orbitals is occupied by two electrons. So these are bonding molecular orbitals, and energy of these I have talked about, energy level diagram. So these are so the wave function is also known, psi1 and psi2. Psi1 and psi2 is the wave function. So if you look at this one, two electron is present here, and you have to find out the electron density at C1. So at C1 the coefficient in the psi1 is 0.372. So 2 multiplied by 0.372 square. Then in case of psi2, you have again two electrons, so 2, and in case of psi2 the coefficient is 0.602, so 0.602 whole square, and this comes out to be, if you calculate it, comes out to be 1. Okay. If you do for calculation for C2, then again you have on the second carbon atom the coefficient is 0.602, and in the psi2 the coefficient is 0.372. And see, what we are doing, a square of the coefficients, so the negative sign will not matter. Negative and negative will become positive. Okay. So what you will get here, 2 into 0.602 square and 2 into 0.372 square, and so the total will be again 1. So obviously by now you know that if you go for C3 and C4, then also you have the C3 and C4, C3 and C3, C4, C4. Both the energy levels will have the same coefficients, and you will have the same value. Okay, because the negative square will also become positive, and everywhere the electron density is 1. So obviously, if the electron density is 1, the charge density will be equal to 0, and so all charge density, therefore all charge density value will become equal and equal to 0. So there is no charge present on the carbon atom of betadiene molecule, and obviously you know betadiene is a neutral molecule. So the result which you are obtain is what is expected from the betadiene molecule. Okay. Now if you go for calculation of bond order, then how do we calculate the bond order? So here I have written the bond orders between C1 and C2 if you have to calculate. Then number of electron, then coefficients of C1 in psi1, and then coefficients of C2 in psi1, plus number of electron, coefficients of C1 in psi2, and coefficient in psi1. In psi1 or psi2, both are psi1, psi1, psi2. It's a fine. Fine. Psi2 and coefficients of C2 in psi2. So what we do? Bond order between C1 and C2. So 2 is the number of electron, and then what is the coefficients of in the C1 in the psi1 for C1 and C2? It is 0.372 and 0.602. If you go back and see 0.372 and 0.602. In psi1 you have these two coefficients. In case of psi2 you have these two coefficients. So only the place of the coefficients will change in the bond order, nothing else. 0.372 is in Psi1 for the C1 and 0.602 is for C2 in the Psi1, but in case of Psi2 the place changes. The 2 is the number of electron, then 0.602 is the coefficient of C1 in Psi2 and 0.372 is the coefficient of C2 in Psi2. So, if you multiply it, what you get is 0.9. Okay. Same way you can do it for C2 and C3. Okay. So, C2 and C3 will have this coefficient 2 into 0.602, 2 into 0.602, then you have here you have the 0.372 and minus 0.372. So, finally what you have is 0.45. Bond order is low here. See, we are not calculating the sigma bond, we are talking about the pi bond, okay, only. And what you know is in 1,3-butadiene you have the double bond character between C1 and C2 and C3 and C4. C2 and C3 will have very small amount of double bond character, and that's why it is bond order is 0.45. That's expected. That's between C2 and C3 the bond order should be less. If you go for C3 and C4, again what the bond order what you get is 0.90. Okay. So, this way all the expected properties of the molecule we have got by HMO approximation for the butadiene molecule. Okay. So, we started with 2 carbon center, then 3 carbon center, then 4 carbon center, and both aliphatic and cyclic, aliphatic and aromatic both we will be doing. Till now we have not done any aromatic, but cyclopentadienyl cyclic molecules we have done. Cyclic molecules we have done. So, we can have a cyclic molecule from this this number of carbon atom also, C1, C2, C3, C4, and that will be cyclobutadiene. So, our next example is cyclobutadiene molecule. So, what we say here is that C1, C2 and C3, C4 are not as strong as the thelinic pi bond. This is also very important, that you don't get a bond order of 1 here. In this case, you don't get a bond order of 1. Here you don't get a bond order of 1. You get 0.9 and 0.9. So, it means it is less stable than the ethylenic bond, the ethylenic pi bond, and we have some double bond character in the C2, C3 molecule also. So, this is an observation which we obtained from HMO approximation. So, this finishes your butadiene molecule, calculation of butadiene molecule, and now we will go for a cyclic system with 4 carbon atom, that is cyclobutadiene. Okay. In a cyclobutadiene system, these carbon are in the cyclic system. Okay. It's butadiene I am saying. So, it means each carbon is sp2 hybridized and each carbon has a 1 pz orbital, and the lobe of the pz orbital is above the plane of the board and below the plane of the board. So, that you should always remember, keep it in your mind. Okay. So, now again here also, though it is a cyclic system, but only 4 carbon atom is present. So, 4 pz orbitals is there. So, 4/4 determinant is obtained from the linear variation treatment. Remember, linear variation treatment, even whenever you need, you can go and find out the see that how do you get the secular determinant. Okay, because linear variation treatment, you write a linear combination of atomic orbitals, wave functions, and then from there you do the variation treatment and you get the secular determinant. So, those of you who have not done it, don't watch this video, go back to the previous module and watch the first linear variation treatment. Okay. If you do then the 4/4 determinant is like this one. In this 4/4 determinant, again you can write in the form of alpha and beta for the HMO treatment, and I've said you that all diagonal element will be alpha minus E for every molecule, be it cyclic molecule or be it this molecule, linear molecule. So, you see all diagonal elements are alpha minus E, alpha minus E, alpha minus E, alpha minus E. Okay. Then in the first row, the second element H12 is bonded, so it is beta, but H13 is not bonded, so it is 0, and H14 is again bonded, so it is beta. In the second row, the first element is beta, that is 2,1, so 2,1 is bonded, so beta, 2,2 is alpha minus E, and 2,3 again will be bonded because 2,3 is bonded, so it will be beta, but 2,4 is not bonded, so it will be 0. In the third row, the first element will be H31, and H31 means 31 is not bonded, so it will be 0. Okay. Then H32 is bonded, so it will be beta. 33 will be naturally alpha minus E, and 34 is also bonded, so it will be beta. Then you will have the last row. The last row is 4,1. 4,1 is again bonded, so beta. 4,2 not bonded, so 0. 4,3 bonded, so beta, and 4,4 essentially alpha minus E. Okay. So this once you have written this one, then replace this determinant for x and 1, and that as we have done earlier. So it will be x for all alpha minus E and 1 for all beta. So x1 0 1, 1x 1 0, 0 1 x 1, 1 0 1 x is equal to 0. So by this solving this determinant will give you the value of x. Okay, and if you solve this value, solve this determinant, again I have done it for all those of you who don't know solving the determinant. It's a given here. So take this term x out and then write a 3 by 3 determinant. Leave this row, omit this row, and then the remaining determinant you write. Then minus, take this one, omit this row, omit this column, omit this row, and write the rest of the 3 determinant. Then take this 0, and if you will multiply by 0 any determinant, it will be 0. So I have left it 0, and then again minus, like minus 1, and remaining determinant you can write. Okay. So if you solve this one, finally what you get is all solutions, every step is given here. So don't bother about, even if you have not done the determinant earlier, you will learn here how to do it, how to find the value of the determinant. Okay. So what you get is x raised to the power 4 minus 4x square is equal to 0, and so what you can write, x square is equal to 4x, x raised to the power 4 is equal to 4x square. So x square will be equal to 4. So obviously, and if x square is equal to 4, then x could be either 0 or plus minus 2 in order to satisfy this equation. Okay. So x could be either 0 or plus minus 2. For this equation, x raised to the power 4 minus 4x square is equal to 0. So x could be either 0 or plus minus 2. So x1 will have minus 2 value, x2 will have 0 value, x3 will have 0 value, and x4 will have plus 2 value. So 4 different values of x we have found. And again you look at here, the x2 and x3 value is 0, x1 is minus 2, and x4 is plus 2. So whatever energy you will calculate, 2 of the energy levels will be degenerate energy levels, that is for x3 is equal to 0 and x4 is equal to 0. We will see it in the next module, calculation of energy, finding out the coefficients, and then extension to other molecules, and then we will be able to finish the HMO theory. Okay. So we did this one, and from this onwards we will talk about in the next module. Thank you.